Hi, I'm a PhD student in the group of Professor Peter Vekelov, and today I'm excited to share my PhD work on solid-solvent interactions. So in the first part of my talk, I will be talking about solid-solvent interactions and its effect on the thermodynamics of organic crystallization. And in the second part, I will talk about solid-solvent interactions and viscosity effects on the kinetics of organic crystallization. So overall, we know that solution crystallization is an essential step in many natural, physiological, or industrial crystallization processes. So whether it's the natural crystals of ice or huge crystals of selenite in the caves of Mexico, or crystals growing in physiological conditions like cholesterol, insulin, kidney stones, and even industrially engineered crystals which has very specific or desired end use, like crystals of zeolite, pharmaceutical drugs like ibuprofen, they all employ solution crystallization. And why I talk specifically about organic crystallization, because organic liquids are extensively used for crystallization, separation, or purification of organic small molecules like active pharmaceutical ingredients. Some of the examples are shown here. And also for crystallization of specialty chemicals like porphyrins, low symmetry crystals of porphyrins, because of their delocalized pi electrons, are used in electronic devices or optical devices, etc. Like it has many use. So it's important to understand the solid-solvent interactions because these interactions govern the pathways and rates of crystallization processes. And we choose an organic molecule, ethylporphyrin 1, as a model solute to understand several different kinds of solid-solvent interactions from a line of 5 organic solvents, again having several different kind of groups to highlight the role of different kind of interactions. So etylporphyrin 1 has 4 polar pyrrole groups as shown here, and it also has non-polar groups like methyl, ethyl, and methine groups. And when we look into the solvent, we have chosen DMSO, which has short alkyl chain length and a very strong dipole moment of its polar group, polar sulfonyl group. And we have also chosen alcohols like butanol, hexanol, octanol, having similar dipole moments of the OH group, but the alkyl chain lengths are increased as we move towards octanol. And we also chose caprylic acid to see the effect of its carboxylic acid group and whether it protonates the positive nitrogen of the pyrrole groups, that is, whether it forms a salt bridge or not. Now, before we go on to determine the thermodynamic parameters of crystallization, we crystallize etylporphyrin by slow cooling from all these solvents. And what we see that it has a plate-like morphology in the alcohols and also in caprylic acid. While in DMSO, it's quite isometric in nature, indicating different rates of growth in different solvents. And when we look into the powder X-ray diffraction pattern, we see that irrespective of the solvent, the crystals obtained are identical to each other. So irrespective of the solvent, the polymorphs of crystals that we get are the same, and they all belong to triclinic P1 space group as identified using Cambridge Crystallographic Database. So in order to determine the thermodynamic parameters, we use the Van 't Hoff's law, which relates the solubility variation in temperature to the enthalpy and entropy of crystallization. So this is a plot of solubility variation with temperature of etylporphyrin 1 when it's dissolved in these 5 solvents. And what we see that it follows an exponential trend, which is quite intuitive. And this is the same plot of solubility variation in temperature. And the slope of these curves give us the enthalpy and the intercept gives us the entropy of crystallization. These are the determined values of enthalpy of crystallization for different solvents. But one thing we know that the crystals which are forming in different solvents are identical. So the enthalpy of crystallization solely depends on the solution enthalpy. So we get an idea of comparative solution enthalpies from this data. This is actually a schematic representation of the comparative solution enthalpy of ethyl porphyrin 1 dissolved in different solution when dissolved in different solvents, and a lower solution enthalpy indicates a stronger solute-solvent interaction. As we go down, the interactions increase in the solution between the solvent and the solutes. So what we see here is that DMSO and hexanol has very similar solution enthalpies. And we conclude that DMSO, because it has a very strong dipole moment when compared to hexanol, even though it has short alkyl chain lengths, because of its strong dipole moment, it has a strong interaction with the polar pyrrole group, which is indicated here in blue of the solute. And its van der Waals interactions, or the dispersion interactions between the nonpolar parts of the solute and solvent, is low, but the polar or the dipole-dipole interactions are quite strong. And when we look into the alcohols, we see that with increasing alkyl chain lengths, as we move from butanol to hexanol to octanol, we see an increase in solution enthalpy with increasing alkyl chain length, and that's even though they have very similar dipole moments. So the dipole-dipole interactions are similar for all the alcohols, but with increasing alkyl chain length, the dispersion interaction or the van der Waals interaction between the solute and the solvent increases, leading to the solution enthalpy trend that we see here. While in caprylic acid, which has a substantial dipole moment when compared to the alcohol, and also a long aliphatic chain, which has dispersion interaction with the nonpolar part of the solute shown here in gray, it has the highest interaction and hence the lowest solution enthalpy. Now we look into the entropy of crystallization data. We see that all of these values are negative, indicating that the solute molecule loses its degrees of freedom upon incorporation into the crystal lattice. And another thing is we see a very similar trend across solvents for the enthalpy and entropy of crystallization, which indicates that the solvent structuring at the crystal interface is only supported by solute-solvent interactions and not by solvent-solvent bonds, unlike aqueous solutions. So in organic liquids, the solvent-solvent bonds are weak, and hence the solvent at the crystal interface is structured only due to the solute-solvent interactions at the crystal interface. And so one thing that we conclude from here is that solvent structuring at the crystal interface is very negligible because of these weak forces of interaction between the solute and the solvent, and the interactions are mostly dipole-dipole interactions and dispersion or van der Waals interaction. In order to understand why caprylic acid has the highest interaction, we dissolved ethyl porphyrin in caprylic and acetic acid, and we measure the UV spectrum. We see that in acetic acid, it has a merged Q band, which is actually a signature of salt bridge formation, while in caprylic acid, the Q bands are all intact, indicating that no salt bridge is actually forming in caprylic acid. Now, an important fact to notice here is the solvatochromic effect that we see in different solutions. In all these 5 solvents where the interactions between the solute solvent are similar, the solution colors are also very similar. But in acetic acid, we see a salt bridge formation, and hence the color is distinct and different. So solvatochromism can be used as a sensitive tool to understand solute-solvent interaction. An important fact to remember. So we understand the solute-solvent interactions. Moving on to the kinetics of crystallization. So the crystals grow by spreading of layers, and these are the layers of crystal. In general, this is just a general example of crystalline crystals growing by formation of layers. And the step velocities are the rate of attachment of solute molecules to the crystal. So it depends, and beta is the step kinetic coefficient, or it is the rate of incorporation of solute molecules into the growth sites. And it depends on the solute diffusivity, and the diffusivity of solute is indirectly or inversely proportional to the solvent viscosity. So the step kinetic coefficient beta varies inversely with the solvent viscosity. And the step kinetic coefficient also depends on the activation energy barrier for molecule incorporation into the growth sites. Understanding this, we move on to measure the step velocities on the O10 face of ethyl porphyrin 1, which is the flat face, and it was identified using single crystal XRD. And we measure the step velocities. So these are actually videos of steps moving in time. So what we see that irrespective of the solvent, whether it's DMSO or alcohols, we see that the growth hillock is very similar, and it grows by and the layers grow by spreading from a screw dislocation, and the step heights were also very similar across the solvents. Now, an important thing is in the alcohols with increasing alkyl chain length from butanol, hexanol, octanol, the solvent viscosities increase, and DMSO is the smallest molecule and it has the lowest viscosity. So we monitor this step displacement in time and we measure the step velocities. So these are the step velocity variation with solution supersaturation. They are all linear. The variation is linear and the slope of these curves give us the step kinetic coefficient. Now, this is a comparison of step kinetic coefficients that we obtained for different solvents. And what we see is with decreasing solvent viscosity, the step kinetic coefficient increases, which is expected, or that is the expectation. But one discrepancy that we see is in case of DMSO with decreasing solvent viscosity, the step kinetic coefficient is actually lower than that of what we see in butanol. And this discrepancy is highlighted even more here, where we see that for the alcohols, the product of step kinetic coefficient and the solvent viscosity is more or less very similar, while in DMSO, it's actually a factor of 2 lower. And in order to understand this, we look into the activation energy. We look into the activation energy barrier, and we try to understand how the activation energy barrier is affected by solid-solvent interactions. Now, in order to understand the activation energy barrier, we must first know that how the solid molecules incorporate into the growth sites, whether it grows by direct incorporation, where the molecule directly comes and joins the growth site at the kink from the solution, while in surface diffusion mode, the molecules first adsorb at the terrace and then it diffuses towards the kink. In surface diffusion, very closely um, spaced steps will have lower step velocity than well-separated steps because closed steps will compete for solute. So we monitor the step velocity here. So we monitor the step velocity of ethyl in octanol for very well-separated steps as well as closed steps. And what we see that irrespective of whether it's a double step or a single step, they have very similar viscosities. And the same trend is seen that the step velocity doesn't depend on the step separation in all these solvents, indicating that it is indeed growth by direct incorporation. So the molecule directly comes and gets incorporated into the kink. And then we use umbrella sampling all atom molecular dynamics simulation to understand the free energy or the mean free potential of molecule incorporation into the kink. Now, looking at these activation energy barriers, we can see that for the alcohols, the activation energy barriers are more or less very similar, and the highest activation barrier can be seen in the case of DMSO. It's actually a 5 kT, it's actually 5 kT more than that of the alcohols. And when we overall, we see a general trend that it has the activation energy barrier has several intermediate steps. And in order to understand the highest activation energy barrier in DMSO, we look into the kink configuration and how the solvents are structured at the kink. So in the kink, it has the polar pyrrole groups of the solutes are exposed, and DMSO being a small solvent molecule, it can have a very high structuring at the kink and a strong interaction with these polar pyrrole groups, and hence the solvent removal before the incorporation of solute molecules becomes difficult, and thus a higher activation energy barrier is seen in the case of DMSO. So overall, I would like to conclude saying that thermodynamic parameters of crystallization can be faithfully evaluated from the temperature variations in solubility. And we have also shown that in this particular case of solute solvent, the solution thermodynamic parameters were mostly dominated by interactions between permanent dipoles and van der Waals forces. And these are weak forces of interaction, and because of which the solvent structuring at the crystal interface is negligible. And we also show that how solute solvent how different solute solvent pairs will have different activation energy barriers for incorporation. And we show that for solvents like the homologous series of solvents, the alcohols, the step kinetic coefficient scales with the solvent viscosity. So understanding these insights into the molecular mechanisms of crystallization help us design robust organic crystallization processes. So with this, I would like to post all the acknowledgements. My advisor, Lakshman, he's the one who did all the molecular dynamic simulation work, and our collaborator at UH, Dr. Jeremy Palmer, and at the University of Strathclyde, Dr. Monica Verzecha. And I would definitely like to thank Doctors Jeffrey Reimer and Caroline Muller for their useful insights, and our funding agency, NSF. And I would encourage each and every one of you to go and check out our paper on solute solvent interactions and how it affects the thermodynamics of crystallization, which was published recently in Crystal Growth and Design. And with this, I would like to thank each and every one of you for your attention. And I would definitely love to answer any questions that you have in the live chat session. Thank you.